Welcome to the operational monitoring demo for distributed tracing sponsored by the Microservice Foundation. Let's start by looking at the official Microservice documentation, accessing the technical overview section and then the event framework section. Let's start by looking at the technical overview of the event framework. On the left, we have a group of microservices that you would generally find within a Microservice deployment. At the top, we have the ML API adapter, which receives HTTP requests for the FSP IP API specification. Below that, we also have an ML API adapter, but this is a handler which processes internal event notification messages, which then sends them as generally callbacks or forwarding messages to external FSPs. Looking a bit further down, we see a similar pattern with the central ledger, specifically an API again, and a handler for processing internal messages for preparing, fulfilling, and managing positions of FSPs. You'll notice something they have in common, specifically a sidecar which handles all log, trace, and audit events which are published to a Kafka event stream. These events are then consumed by the event stream processor, which mediates and translates the messages into our F stack. That means Elasticsearch, FluentD, Kibana, and Apm. The ingestion of these events within Elasticsearch allows an operational team to easily filter and query these events. We also send the trace events to Apm. This allows us to construct a distributed trace graph and visually see a representation of the actual processing flow of a transaction, specifically a transfer, for example. I will show you this a bit later, and also how we can link the distributed trace graph and those specific spans to the log events that get ingested into Elasticsearch. But first, let's just have a look at our microservice architecture in more detail. If we consider one of the microservices that we had previously, that can be represented in Kubernetes by what's known as a pod. A pod has several containers. In this case, we have the service itself that's represented here. That could be, for example, the ML API adapter, and below that, we have the event framework sidecar. Those are tightly coupled together in Kubernetes, what's known as a pod, which is a single unit of deployment. That guarantees that the sidecar and the actual service are always deployed in the same machine. Additionally, here we can see components of the event framework itself. This is a reusable library that is implemented by both the service and the sidecar, and provides a gRPC client and server. By using this protocol in conjunction with pods for deployment ensures a very low latency communication overhead. Let's talk about distributed tracing. Below, we have the event flow diagram, which shows how two services interact with each other. Let's break some of these elements down. First, we have a trace. This represents the end-to-end flow of a distributed trace over distributed components, like service A and service B here. Below that, we have a span. This is the primary building block of a distributed trace. It represents an individual unit of work done in a distributed system. This is a specific type of span known as a parent span. That means it may have a child span. In other words, a span that leads off from that particular piece of work into another piece of work. And that may be within the same service or distributed in another service. Each span at a minimum is represented by a start and an end event, with the end event containing all the necessary information to describe the span itself, the relationship to the parent, as well as how it's associated to the trace. This is known as a trace event, and this is what's ingested into Apm. In Microservice, we record other events during the lifecycle of a span, specifically logs, errors, and audits, with audits, for example, being ingress and egress events, which are associated to the start and the end of the span. These events are ingested into Elasticsearch under an index called Microservice. Let's look at an example event. First, let's look at the metadata. Here we have an identifier that's specifically for the event itself, and an associated action. In this case, there is a span representation of a trace. In audits, it could be an egress or an ingress. Above that, we have a content area where we can store anything from headers, payloads. However, this is more likely used for logging and for auditing, not so much for traces. At the bottom, we have the trace metadata. In here we have the service field, which is the name of the actual service where this trace was recorded at, followed by a trace identifier, a parent span identifier only if this is a child span itself, which is subsequently followed by the span identifier itself for this particular piece of work. And below that, we will see the start and end times for this particular span. Lastly, we have tags. These tags represent additional context for the trace itself. For example, we have a transaction identifier, we have a transaction type to describe the ID itself. For example, here it is a transfer identifier. And below that, we have some information about the parent span. Here we can see that the parent event type and action have both been captured. In this document, we also describe the HTTP transport specifications that are required for tracing. Specifically that we support the W3C HTTP header standard. Feel free to consult the specification itself. But it comprises of two main components: a trace parent, which is representative of the trace ID and the parent span itself, and an optional trace state that provides support for vendor-specific trace information, as well as additional contextual information for multiple distributed traces. An example of this being a transaction that spans from a payer FSP to a hub modular switch to a pay FSP. Let's move on to the demo. We can access Elasticsearch through Kibana as well as the Apm Dashboard. Apm stands for Application Performance Monitoring. In this dashboard, we'll be able to see the distributed trace captured by the modular switch itself. This empty dashboard represents an event stream processor that we use in one of our development environments. Let's use modular testing toolkit to send some transfers into our dev environment. I will be using the P2P money transfer use case for the happy path. This is comprised of the get parties call, a post quotes, and a post transfers. Let's click the run button. The test case was successful. Let's go have a look at the Apm dashboard. Moving back to the Apm dashboard, at the top we can see information like latency and throughput. Let's go through some of the traces and spans that were recorded as part of the P2P test case. Here we have the master transfer trace. This represents the full end-to-end transfer. Next, I've highlighted some of the spans that form part of the master transfer trace. Each of these represent a microservice within the modular stack, ranging from the ML API adapter all the way to the central ledger components for handling prepare, fulfillment, and position management. Let's click on the master trace. At the bottom of the page, we can see the distributed graph. At the top, we have the master transfer, which represents the full end-to-end transaction. Below that, we have several spans. Starting top left, just below the master transfer, we have the ML transfer prepare. This represents the ML API adapter receiving the transfer prepare request. If all API validations pass, the message is then published and then consumed by the CL transfer prepare component. This is the central ledger prepare handler component. This will do business validations against the transfer, such as validation checks, as well as ensuring the FSP participants are onboarded on the switch. Once the transfer has been accepted with its state persisted, an event will be published which will be consumed by the central ledger position management component, which will reserve funds for the payer FSP and update their position accordingly. An event will then be consumed by the notification event component as part of the ML API adapter. This is comprised of three spans, which you can see here: the main ML notification event itself and two child spans. The first being the get endpoint, which represents the call to the central ledger admin API to fetch the endpoints for the notification itself for the payee, as well as the actual send request span, which is actually physically sending the notification to the payee FSP. The pay FSP would then process the transfer request, commit the funds, and respond with a transfer fulfill callback. This would be received by the ML API adapter service component, which would validate the request against the API specification Similar to before, the CL transfer fulfill component now will then process that event. This is the central ledger fulfill handler component. Additional business validations are carried out here, including the crypto condition fulfillment check. This is followed by the central ledger handler component processing the fulfillment event, resulting in the final commitment of funds, as well as updating the payee position. Finally, the notification event will then be processed, with the fulfill callback being sent to the payer FSB as a final confirmation. We can click on each of the spans to see more detail. Let's click on the ML transfer prepare. In this panel, we can view the detailed information for the span, including its trace information and associated metadata, such as the labels here, which include details such as the payer and payee FSB, the trace state, the transaction ID, and the transaction type. In this example, as we expect, the transaction ID is of a transfer type. If we click on the action dropdown, we can then click on the View Sample Documents. This will take us to Kibana's Discovery Dashboard, where we have access to all logs and events ingested into Elasticsearch. This view has been pre-filtered as a result of clicking on the View Documents for the ML Transfer Pair span on the previous screen. In the filter box, we can see the trace ID and the span ID with their associated values. Take note, Apm uses the term transaction instead of span. However, in Mojaloop we prefer the term span, which is more commonly used by tracing standards, such as the W3C specification. The far left panel offers additional filtering options, including the tags, otherwise known as labels in this context, that we observed in the transaction detail screen. Above that, we have an index selection dropdown. Here we can see Apm, which is selected by default. In the main panel, we have a list of all the trace events that were ingested by the Apm index. In this case, we only have a single entry that represents the ML transfer prepare span. Let's select a different index by clicking on the index drop-down selection box. Here we see three different indexes: Apm, which we've already discussed, Logstash, which is used by our dev environment to capture all Kubernetes and pod logs, the last being Mojaloop, which is used to ingest all event framework events such as logs, audits, and traces. Let's select the Mojaloop index. Let's remove the span information from our filter query. The main panel will now list all events, including logs, audits, and traces that were ingested by the Mojaloop index for the currently filtered trace ID. This is reflected by the event type options on the far left panel, where we can see options for audit, trace, and log. Above that, we can see the options for filtering the event action. For example, you can see span, start, egress, and debug. We can find out more information on these types and associated actions by referring to the Event Framework documentation, section 3.2 Schema Definitions. For each of the event types, we have a list of applicable actions. For logs, we have actions that represent log levels such as info, debug, error, etc. For audits, we have actions representing the start and end of traceable processes within Mojaloop. We also have actions for both ingress and egress internally or externally. For example, internal events being published to Kafka, another being external notification callbacks to FSBs. And finally, for trace, we only have a single action representing a span, specifically the record of a span. Going back to the demo, let's select a start span. Notice if you hover over the metadata event type, only audit will be displayed. This is because we have selected the start action that solely belongs to the audit event type. Similarly, the metadata trace service below will only be populated with span names that contain a start audit event. Let's select the ML transfer prepare. Just below the query box, we can now see the filters that we have selected. In the main panel, we have a single result, with yellow highlighted fields matching our selected filter. Let's expand the result and its content field. Here we have the transfer prepare request sent by the payer FSB and received by Mojaloop. It contains the full header and payload of the incoming request as audited by the ML API adapter. Let's remove those two filters. Let's see if we can find the put notification from the Mojaloop hub to the payer FSB. First, let's filter out the event action as an egress type, followed by the service type for ML notification events. We are then left with two results. The first being for the transfer fulfilled callback from the switch to the payer FSB, and the second being the post transfer prepare request from the switch to the payee FSP. Let's have a look at the content field of the put callback. Inside the content field, we can see the URL of where this notification was delivered, specifically the dev2 simulator. We can see the method, which is a put. We can see the associated headers, as well as the data or payload. And inside, you can actually see the completed timestamp, the transfer state, and the fulfillment. Let's consider another scenario. Going back to the transaction screen, I've added a filter for labels.errorcode against a wildcard. This returns a single master span called post participants. Top right, you can also see there's been an error in the throughput diagram. Let's select the post participant span. We are now presented with a distributed trace graph showing the parent span, i.e. post participants, representing the post participant interaction from an FSP via the account lookup service, and a child span representing the subsequent post request from the account lookup service to an Oracle to register a party for the requesting FSP. We can now also see an error indicator on the parent span. If we open up the transaction detail for the parent span, we can see the error details on the metadata labels, which includes the error code, the error description, and the source FSP of the request. In this case, there was an issue with the communication between the account lookup service and Oracle. For our final scenario, let's go back to the Moduloop testing toolkit. You can fetch the event logs directly from Elasticsearch by clicking on the Server Logs button. This interaction is facilitated through Elasticsearch's API. Let's look for the ML transfer prepare event, and here we can also see the header and the payload contents. If I copy that transfer ID and go back to the transaction dashboard, I can actually add that as a filter. Take note of the autocomplete feature as I type this in. After refreshing the page, the transactions at the bottom of the screen are now displayed only based on that transaction ID. Thank you for listening. I am Miguel de Barros from Modusbox, a Moduloop principal architect working on the open source funded development project, part of the team designing and engineering core Moduloop services over the last 2 years, and a member of the Moduloop Design Authority.